Hello again. We're going to continue talking about the relationship between the first derivative, the second derivative, and the graph of the function. First, let's summarize what we said last time. We have a derivative, first derivative, second derivative, and the function. And we're looking at the graphs of these. Particularly, we want to look at the graph of the function. So, if the first derivative is positive, we know the function is increasing. Okay. But the second derivative could be positive or negative. If the second derivative is positive, then the function is concave up. So it's increasing and concave up, it's got to look like this. If the second derivative is negative, but the function is still increasing and concave down, so it's increasing but it's concave down, it would look like this. If the first derivative is negative, then the function is decreasing, right? If the second derivative is positive, then the function is decreasing and concave up. So what would that look like? Like this. Decreasing but concave up. Then if the first derivative is negative, the second derivative is negative, the function is decreasing and concave down. So it's decreasing and concave down, so it's looking like that. We also said if the function goes from increasing to decreasing, then there's a local maximum. If the function goes from decreasing to increasing, then there's a minimum. If the second derivative changes sign, S-I-G-N, then we have an inflection point. Okay, so let's look at another kind of problem. Last time we talked about given the graph of the function, you have to tell where the first derivative is positive, where it's negative, where the second derivative is positive, where the second derivative is negative, where there's zero. You have to do all that. What if you're not given the function? What if you're given the derivative, a graph of the derivative of the function? So let's say I'm given a graph of the derivative, not the original function, but the derivative of the function. Let's do this. What if I'm given that and I say that's not a picture of the function, that's a picture of the derivative? Now we've got to indicate where the function is increasing, where the function is decreasing, where the function is concave up, where the function is concave down. So where meaning on what intervals? So let's say this is -2 to 2. And this is at 0. So let me just do that again so it looks a little better. Okay, so this is 0, this is -2, and this is 2. Okay, so now remember, we're being asked about the function, not the derivative. We're given information about the derivative. Okay, so first we have to decide where's the function increasing. Well, the function is increasing where the derivative is positive. Where is the derivative positive? Above the x-axis, from negative 2 to 2. So the function is increasing from negative 2 to 2. The function is decreasing from negative infinity to negative 2 and 2 to infinity. If we assume that this is continuing down here, it's not stopped. Why? Because the derivative, which is this, is negative here and here over this interval and this interval. It's positive there. Okay, so let's, before we get to concavity, what if we identify local min and max? So f has a local min. It's got to be where, well, it's got to be where the derivative is 0, which is here and here. So we got to figure out what they are. They're local mins or maxes. At negative 2, we go from a negative to a positive derivative. So our function goes from decreasing to increasing. So we have a local minimum at x equals negative 2. We have a local maximum at x equals 2. Because our derivative, we always read left to right, our derivative goes from positive to negative. So it goes from, the function goes from increasing to decreasing. Okay, now second derivative. We need to figure out where the second derivative is positive, because then we can determine where f is concave up. So we want to determine where f is concave up. So we need where the second derivative, the derivative of this is positive. Well, the derivative of this is positive where this is increasing. It's increasing from negative infinity to 0. So this f prime is increasing from negative infinity to 0. So f double prime will be positive. So f is concave up. F is concave down from 0 to infinity. Because from 0 to infinity, the derivative of this, the slopes of the tangent lines, are all negative. So we have an inflection point at x equal to 0. Because we change from concave up to concave down there, and that's an inflection point. So we could propose a graph for the original function. The original function is increasing on negative 2 to 2. It's decreasing from negative infinity to negative 2 and 2 to infinity. So it must be looking like something like, oh, whoa. Try this again. Something like this. It's decreasing. We get to negative 2. The function is decreasing. We get to negative 2. Then it's increasing here. And then it's decreasing again after 2, so it hits a local maximum, local minimum, local maximum. We don't know where on the graph this is. It could be up here, it could be down here. We don't know the actual f values. We don't know the actual y values. Notice too, this f is concave up from negative infinity to 0, and then it's concave down. So right here at x equal to 0 is an inflection point. So we can get information from about the graph of the function from the graph of the first derivative. So The problems you have to do include, by Wednesday night, include these. You have from this chapter, which is chapter 3.3, you have numbers 1, 2, 5, 6, 7, 8, 9, 11, and 13. Now, what I'm going to do is stop this video, but I'm going to put another video up where I do problem 10, which is very much like 11 and 13.